Today we'll finish this long topic. I broke it up into two parts because it's so long. What that we want to do, it's actually, I think, the most important part of second order differential equations. When you have linear equations with constant coefficients and right-hand side found in that table of undetermined coefficients, or the sum of terms found in the table, those are problems you want to be able to solve in lots of the sciences. That's what this is, right? Constant coefficients, a number times the derivative, a number times the derivative. Sometimes there's a y times a number. So that's the constant coefficients linear equation. And on the right-hand side, each of these things comes out of that table of undetermined coefficients that we put up before. And so I just want to remind you first what we were doing in the previous video to solve these things, because what we're going to do mostly today is extend it and say, well, what if you don't have constant coefficients? Or what if you don't have a right-hand side in the table? Then there's another technique we use called variation of parameters. So here's what you do for this important case of constant coefficients and right side of the table of undetermined coefficients. It's three steps. One, you solve the associated homogeneous problem, also called in some texts the complementary problem, where you just replace the right-hand side with 0 and you have constant coefficients equals 0. This equation can always be solved by our previous technique of the characteristic equation. Here we've got r squared plus r equals 0 is the characteristic equation for this differential equation. That factors is r times r plus 1 equals 0, from which you deduce that r can be 0 or negative 1. Are the two solutions to this equation. That means the two corresponding solutions of the differential equation are e to the 0t, which is just 1, and e to the minus 1t. And the general solution of this homogeneous problem, where you replace the right side with 0, is c1 plus c2 e to the minus t. Now we need that as part of the solution of this problem. Let me move this up a little bit. The second step we have to accomplish, maybe I can still keep the original problem in there. Maybe. Is to find a particular solution. That just means any solution. Any solution whatsoever of the original problem. That's step 2, find any solution with the right-hand side not 0. And then the third step will be add the two together. Take this general solution of the homogeneous problem plus one solution of the non-homogeneous problem. Their sum is the general solution of the non-homogeneous problem. That will be step 3 next page. So what's the particular solution look like? You have to look at each of these terms. If you look back at the table of undetermined coefficients, when you have on the second line of that table a constant times e to the alpha t in general, if that's the right-hand side, you look for a solution that's a constant times e to the same alpha t. So a constant times e to the 1t, you look for a constant times e to the 1t, but it's usually a different constant. So we're going to try a particular solution plugging this in, and if this were the whole differential equation, there would be a solution in this form, unless this is a solution of a homogeneous problem, meaning we need to multiply it by t. And if it's still a solution of the homogeneous problem, then we should multiply it by t squared. And if that's still a solution, we multiply it by t cubed. Until we get something that doesn't look like this, then we know by the table of undetermined coefficients there will be a solution to that form. So I suppose I'm just solving this problem with no 3 on the end. And I say, will this be a solution of a homogeneous problem? No, because there is no e to the t. There's an e to the minus t, but that's a different exponential function, right? So constant plus constant times e to the minus t can never be equal to a constant times e to the t. So this will be the formula solution if this were the differential equation without the 3. Now you look and say, well, suppose it was just the 3 and not the 2e to the minus t, then what would be the formula solution? And the first line of the table says if you have a 0th degree polynomial like that, there will be a solution that's a 0th degree polynomial, just a constant gamma 1. Unless that's the solution of the homogeneous problem. But it is, right? If I just have a constant, I can put c2 equals 0 here, and that shows that a constant is a solution of the homogeneous problem. I won't be able to put gamma 1 as a particular solution to this problem, because if I put a constant in here, it always makes the right-hand side 0, right? These are all the solutions that make the right-hand side 0. So I can't use a constant. This term here would be a solution to the homogeneous problem. So I multiply constant times t. Now is it a solution? None of these things, no matter how I pick C1 and C2, is equal to a constant times t on the interval. They're linearly independent. So I now know that if this were the problem, just 3 on the right, there would be a solution of the form of constant times t. Not just a constant right here, but because that would solve the homogeneous problem. Alright, so now if I want to solve with the right-hand side the sum of these two terms, I look for a particular solution that's the sum of these two terms, because this one alone would satisfy this problem. This one alone would satisfy this problem, and the sum together will satisfy this equal to the sum of the two. So I look for a solution of this form, I plug this into the differential equation and see what gamma 0 and gamma 1 have to be. Alright? So in order to do that, I need the derivative, so I just take the derivative, it's gamma 0 e to the t plus gamma 1. And then I take the derivative of that, I get gamma 0 e to the t as the second derivative, and I plug those into the differential equation. Y double prime plus y prime equals 2e to the t plus 3, where here's, I've put in y double prime from here, and y prime from here. Alright, y double prime plus y prime equals the right-hand side. Now what you do on all these problems is you group like terms. Some of the terms have e to the t, and some of them are just constant terms. So there's a gamma 0 e to the t, and if I subtract this one over, minus 2 e to the t. So if these are all the terms with e to the t, once I run these over here, subtract 2 e to the t plus 3 from each side. And so then there's constant terms, right? There's gamma 1 and a minus 3 subtracted over. So all this has to be equal to 0, but now e to the t and 1 multiplying this one are linearly independent functions. The only way you can make this be equal to 0 on an interval with linearly independent functions is if their coefficients are both 0. So 2 gamma 0 minus 2 has to be 0, gamma 1 has to be equal to 0, and we get, from those two equations for the two constants, there they are. Gamma 0 must be 1, and gamma 1 has to be 3, right, out of these two equations. Consequently, putting those back into yp, I get 1 e to the t plus 3 is a particular solution. Now, if I have the general solution of the homogeneous problem, and the particular solution here, I just add them together. Here is the form of all solutions to the non-homogeneous problem. There's our general solution that we were looking for. Alright, so we did that last time. This is just another example. Now what we want to do is say, what if that doesn't work? What if the right-hand side is not on the table? Or what if the left-hand side does not have coefficients in constant coefficients in a linear equation? Then we'll try this technique called variation of parameters, and this one gets you a particular solution in some other cases. Unfortunately, to be able to apply this method, you already have to know the general solution of the homogeneous problem, which can be tricky, so it only works if you can solve the homogeneous problem already. But a non-homogeneous problem, you can find a particular solution to go with it as follows. If you know two independent solutions, y1 and y2 of the homogeneous problem, with the right-hand side equals 0, which, if you know those, then C1, this one, plus C2 times this one gives you the general solution. Then you do this. You look for a solution, y particular equals y1, the first solution that you found of the associated homogeneous problem, times v1, plus y2 times v2, where v1 and v2 are unknown functions. You're going to try and find them. Right? And it turns out that if you put v1 equal to this integral and v2 equal to this integral, it works. There is a particular solution to that form, and in these formulas, w refers to the Wronskian. y1, y2 in the first row, and their derivatives in the second row. So here's the proof. You'd say, why does that work? This is why it works. You just try the method. You say, suppose yp is y1, v1 plus y2, v2. What would v1 and v2 have to be to get a particular solution? Well, I take the derivative. I get this by the product rule, right? Derivative of the first times the second plus first times derivative of the second is this. Same thing over here. Product rule for this one is these two terms. And now we'll make an additional assumption and hope we can get a solution. But if this is also true, that y1 v1 prime plus y2 v2 prime is also equal to 0, That'll make my problem easier because these two terms will drop out. I'll just have this. So I'll make the assumption that yp is of this form and this is equal to 0 and hope it works. You know, you play around with this for a while and be clever and figure out you can get away with that. But you just try it, and then yp prime becomes this. And you can take its derivative and get yp double prime. Again, the product rule in this one gives double prime times v1 plus y prime v1 prime, and so on. This is the product rule for this term and this term, those four terms. Now you plug these into the differential equation. Here's the second derivative right here. Second derivative plus p of t times the first derivative plus q of t times y equals f of t. I just plugged it into this differential equation we're trying to solve. Y double prime plus p of t y prime plus q of t y equals f of t. I plug that in. Y double prime plus p of t y prime plus q of t y equals f of t. And now I try and group my terms that have v1 in them. Just by algebra, and it's these things, all the terms with v1. I group all the terms that have v2 in them. Here's all the ones with v2. And then all the terms that don't have anything equals f of t. Then we notice that since y1 and y2 were solutions to the associated homogeneous problem, what does this have to be? y1 double prime plus p of t y1 prime plus q of t y1. The equation, since they're solutions of the homogeneous problem, the right side 0, this is 0, right? That was the homogeneous problem. This plus this is 0. Same thing here. This is 0 because y2 was assumed to be a solution of the homogeneous problem. That's why you need the homogeneous solution to apply this method. You have to know two solutions, independent solutions of the homogeneous problem. All right, so these two fall out and you just have this equation, right? There it is, what's left. And now, can we solve this? Yes, we can. This equation amounts actually to two linear equations for v1 and this one with the assumption up here. This one and this one together is a system of two linear equations for the two unknowns v1 prime, v2 prime, right? So you apply, if you've seen linear algebra, Kramer's rule, and what it says is the system, or you can add a multiple one equation to the other to eliminate coefficients. So it's messy, I don't want to do that. Let's just say Kramer's rule, but you can always solve these two linear equations with two unknowns. This is elementary linear algebra. You get these two solutions, where W1 and W2 are the Wronskian, right? It's Y1, Y2 prime minus Y1 prime, Y2 is what the Wronskian is, recall. Now, if V1 prime and V2 prime are these functions, these are all known, right? This F was the right-hand side of the differential equation. Y1 and Y2 were solutions you found. So you know what these functions are. You just integrate them and you get V1 and V2. That's where the formula came from. That's the derivation of variation of parameters. If you have a differential equation of this form, and when you put the right-hand side equals 0 to get a homogeneous problem, you can find two independent solutions, Y1 and Y2, with P, Q, and F continuous is assumed in here. Then, a particular solution is always of this form, V1, Y1 plus V2, Y2, where Y1 and Y2 are the solutions of homogeneous problems you found, and V1 and V2 are these integrals. What variation of parameters amounts to after all that stuff is a formula. You can see how complicated this is. You don't want to do this every time. What you do is memorize the formula, and then you just plug it in to find a particular solution when you can't apply constant coefficients, which is evidently easier, right? When you can use it. This actually does work in place of constant coefficients. You can do this instead. It's just longer, right? It's easier just to look something up on the table and plug the thing in. So this is really for cases where you just hard out because you don't have constant coefficients and don't have the right side of the table. So let's see. Here's an example. Y double prime plus 4y equals tangent 2t. Why couldn't we solve this one before? It's because tangent wasn't in the table, right? It's had sine and cosine. So this isn't in the table, but it is constant coefficients. Maybe we can solve this with variation of parameters. We just go to the formula. That's all variation of parameters is. We say that we know how to solve the associated homogeneous problem because it's constant coefficients, right? We solve the homogeneous problem y double prime plus 4y equals 0. Has characteristic equation r squared plus 4 equals 0 with solutions r equals plus or minus 2I. So we recall that the solution when r1, r2 are plus or minus 2I, two complex conjugates, pure imaginary conjugates, then cosine 2t, cosine and sine 2t are two independent solutions, and the general solution is c1 cosine 2t plus c2 sine 2t. I won't go through the details of that one again. That was when we solved homogeneous problems. R squared plus 4 equals 0 had solutions plus or minus 2I, and so the differential equation had this general solution. Now, I have two independent solutions, cosine 2t and sine 2t, so I can apply variation of parameters to the non-homogeneous problem. F of t equals tangent 2t with the right-hand side. I compute v1 equals minus integral y2, right, the second solution, times v times the f over the Wronskian of these two functions. And v2 is y1 times f, right, y1 times the right-hand side of the equation over the Wronskian of the two functions. What's the Wronskian of cosine 2t, sine 2t? Well, you put the functions in the first row and their derivatives in the second row. This times this minus this times this is the determinant. Is 2 cosine squared plus 2 sine squared is just 2, right, by trigonometry. Pythagorean identity. Now, v1 was this. Becomes, well, the Wronskian is just 2. I pull that 2 out. And sine times tangent is sine squared over cosine. I will rewrite that as sine squared over cosine, sine times tangent. This is where your integration gets difficult sometimes. This one is actually not so easy. But what you can do here is, there's a couple ways to do it. Replace sine squared with 1 minus cosine squared. And then 1 over cosine t is secant, right? So if I write this is 1 minus cosine squared over cosine. 1 over cosine is secant, and secant is an integral, you know. It comes out to be ln of secant plus tangent times a fourth. Since it's not secant t, it's secant 2t. So this is the integral of secant. And then cosine squared over cosine is, well, minus cosine squared over cosine gives you integral of minus cosine comes out to be minus sine. So there's the tricky integration that goes on. And you get v1 as that. v2 is a little easier. v2 came out to be integral sine 2t, which is just times a half, which is minus a fourth cosine 2t. All right, now we got it. Yp was equal to v2, let's see, I'm sorry, y1 v1 plus y2 v2, right? First solution of the homogeneous problem times v1 with it, we integrated. Second solution, added the second solution of the homogeneous problem times the second thing we got by integration. Add all those together and we get minus a quarter cosine 2t ln of secant 2t plus tangent 2t is a particular solution. Variation of parameters doesn't solve the whole problem like this. It gives you a particular solution. Now we have the general solution of the associated homogeneous problem still. We add those two together, yh plus yp, and get the general solution of the non-homogeneous problem. So there's what you do when you have a more complicated problem than what we were doing last time. Here's another kind of problem you run into. This one is in constant coefficients. This is called an Euler equation when you have 0 on the right-hand side. T squared d squared y dt squared minus 4t dy dt plus 6y equals this. How can I solve that? Well, we're going to do Euler equations shortly, but for now, we'll just say that it turns out that the homogeneous problem has solution c1t cubed plus c2t squared. All right, so that's the And the problem with this one, this right-hand side actually is in the table of undetermined coefficients, but unfortunately this isn't constant coefficients, so once again our previous technique doesn't work. But what we can do is, it turns out that this homogeneous problem, by putting the right side 0, isn't a kind of equation that can be solved. We'll do shortly, called an Euler equation. So its solution turns out to be this. That means that t cubed and t squared are independent solutions to the homogeneous problem. We can use those to find a particular solution to the non-homogeneous problem by variation of parameters. Here's what we do. We compute the Wronskian. T cubed and t squared are two independent solutions of the homogeneous problem. Their derivatives. It's this times this minus this times this, and you get minus t to the fourth. Right? You get v1 and v2 by integration. Right? You take minus y2 times f over the Wronskian, and it comes out to be this integral. v2 is y1 f, the right-hand side f over the Wronskian, and you integrate it and you get this, and it's just a formula. From the Wronskian, integrate to get v1 and v2, take v1 y1 plus v2 y2, those things you know, and that gives you a particular solution. Voila, right? So a particular solution looks like this. We add that to the general solution of this problem, the Euler equation, and there's the general solution of our non-homogeneous problem. Well, there's one more technique. I'm going to put it off for now. Try some of these problems with variation of parameters. Well, one last method. This is called reduction of order, and it turns out to work for both homogeneous and non-homogeneous differential equations of second order that are linear, if you can just find one solution to the homogeneous problem other than the zero solution. So one independent solution of the homogeneous problem. This one, I'll just go with the formula. If you have one solution, y1 of t, of a differential equation of the same form we did as for variation of parameters of the homogeneous problem. In other words, if I have one solution, y1 of t, that when the right-hand side is 0, I can actually solve this problem. It sounds better than variation of parameters, right? Variation of parameters, and you need two independent solutions. Well, it is if you can do all the integrals. This one requires a little extra integration is all. So if you can't make it with variation of parameters because you don't have two independent solutions, all you have to do is be able to lucky guess one, and sometimes that happens. Sometimes you get one of these linear equations, you play around with it, you can think of something simple that maybe you can plug in and solve it when the right-hand side is 0. That's an easy right-hand side, isn't it? And sometimes you can guess one. If you can guess that one solution, you can always write the general solution in this form, at least as an integral. And if you can do both these integrals, then you're home. You've got the solution to a homogeneous, if the side is 0, or even non-homogeneous problem. And here's the formula. I won't derive this one, but it's similar to variation of parameters. You just assume a solution in the form y equals y1 v1 exists, and when you plug that in, and like we did with variation of parameters, you come up with this formula. That y1 times 1 over mu y1 squared integral mu y1 f, where f is the right-hand side, gives you the general solution as long as you carry the arbitrary constants in here, where mu is e to the integral p of t dt out of the original equation. All right. Now, suppose I just apply it to this one. So once again, it's just a formula. Suppose I have this, because the derivation is too long anyway. Suppose I have this differential equation. This one, again, is an Euler equation if you had 0 on the right-hand side, turns out. But suppose I can just kind of play around with it. I think, boy, there's powers of t. Maybe I can make a power of t satisfy, and I figure out by hook or by crook. Actually, t squared satisfies this when the right-hand side is 0. All right? So if t squared satisfies with the right-hand side is 0, I can use reduction of order to solve the equation. Homogeneous or non-homogeneous. This one's non-homogeneous, right? It's not 0 on the right-hand side. So what I'll do is I can, well, I go this formula. and say, well, y is y1 times 1 over mu y squared integral y mu f dt, where mu is equal to integral p of t dt. For this differential equation, p of t was minus 4t, right? So whatever multiplies dy dt is p of t from the differential equation. So I take first mu equals e to the minus, and very important, you have to put this into standard form first. P of t is not minus 4. You divide through by the lead coefficient to put it in standard form, but this doesn't work. You divide through by t squared, and p is minus 4 over t, right? And so mu is e to the integral of minus 4 over t dt. You integrate this, and you get minus 4 ln of t, e to the minus 4 ln of t. Put the minus 4 up, and e to the ln of minus t to the minus 4 gives you 1 over t to the fourth. So integrate this and see. Now, I can put that in for mu here in the formula, and I've got y1, the first solution I found t squared, times 1 over y1 squared. Well, y1 squared is t squared, so that's t to the fourth, and then mu is 1 over t to the fourth, gives me a t to the fourth on top. So 1 over mu is t to the fourth, 1 over y squared is 1 over t to the fourth. Integral of y1, which is the t squared, mu, which is the 1 over t to the fourth, f of t, the right-hand side of the equation, was 6t squared minus 1. This is easy to integrate, right? It's just the power rule, and you get 6 minus 1 over t squared. Oh, I'm sorry, the integrand is 6 minus 1 over t squared. And a little integration work, you wind up with 3t to the fourth plus t squared ln t plus c, and then if you carry the arbitrary constant out of integration, this one gets you a c1, and when you integrate it again, c1 becomes c1t, all times t squared gives you this one, and then the integration constant out of this one, c2, is multiplied by t squared gives you this one. And what do you know? You have the general equation. What you have is that this is a particular solution. T squared was the solution we guessed coming in. And we found out as a bonus, t cubed is another solution of a homogeneous problem. This would have been the solution of a homogeneous problem by itself. Since we had a right-hand side of the equation, we also got this as a particular solution to the non-homogeneous problem. So there it is. Reduction of order can solve a homogeneous problem, could be this, or it can solve the non-homogeneous problem. We put f equal to whatever function you could, provided you can do the integrations and guess y1 before you begin. This one allows you to solve the same differential equation we did with variation of parameters, only knowing one solution of the homogeneous.